and they liked that name, and they used it, and it stuck. So it's still called the Ho Chi Minh Surf Trail in San Diego. This I thought was really good. So there's a yeast factory in San Diego that makes the yeast that most craft brewers use. And of course, yeast comes in many different kinds. And so what they have is they have a tasting room. And you could have a beer, but you could have the same beer with like several different yeasts to tell the difference. So you can see the difference that the yeast makes in the taste of the beer. And so you get a flight of beers, same beer, several different yeasts. Looks really interesting. I know we have a lot of beer fans in the Connect crowd, and I thought this really sounded novel. How much does yeast affect the taste in your beer? Do you know? Okay, so two really good keynotes this morning. Brent Gourde from ARM and Jeremy Hallam from the University of Michigan. Brent's going to share with us on HPC, and Jeremy's going to talk about data science. So please join me in welcoming Brent Gourde.
Thank you. So I have to admit that I'm a local, so for me it was a drive down here, which is nice. And it's funny to see all of these things going on, what you can do when climate is not really getting in your way of life. You can do topiaries, you can do yeast tasting in beer, you can surf. It's nice being here. The one question I want to ask the crowd is how many people here think that it's cold outside if you're from Texas and it's pleasantly nice and not 1,000 degrees? And how many people are from northern climates where you think it's warm outside? It's one of those three bears things, right? I came here enough times to think it's just right, so I'm moving here. So I'm going to talk a bit about HPC. As many of you probably know, ARM is starting to make inroads into high-performance computing. It matches with my background. There is a huge amount of leverage going on in what we're doing in high-performance computing, huge. And we're standing on the backs of giants. We're literally taking advantage of much of the work that you're doing here to elevate us in high-performance computing and let us attack some of the world's toughest problems. And as hopefully I'll get across in this talk, some of the new architectures that are coming our way on the internet. HPC is generally thought of as pushing boundaries. HPC is a really good community to engage with when you have a new technology. The community is exceptionally tolerant of stuff that almost works but doesn't quite. You got to kind of stand like this to make it work. The community that I come from is really good at being able to make use of early stage products, and I'll show you a couple of slides as to what's been going on there. My background, I started doing high-performance computing in the mid-'80s in Canada. I'm actually an immigrant. I like to tell folks that I'm an environmental refugee moving from the prairies of Canada where it was 40 below to San Diego where below doesn't actually come about. I've spent about 15 years in the US National Laboratories, mostly Lawrence Livermore National Laboratory, but the Office of Science Laboratories as well. I was responsible at Livermore for an architecture called the Blue Gene architecture, which was a project with IBM in the early 2000s where we took, at the time, Beowulf clusters were growing to be on the order of 10,000 nodes, and we took that and scaled it up to 150,000 nodes with 6 million way parallelism and that sort of thing. If you were here for Satoshi's talk yesterday, he mentioned that their machine has more nodes than Blue Gene, and that's what he was referring to. The Fugaku machine has 7.5 million cores in it. Imagine writing an application that harnesses the power of 7.5 million processes at the same time. Pretty quick, you run into an issue called Amdahl's law, where any serialization in your program means 7.5 million minus 1 are sitting idle. And so it takes a lot of heroic effort to make use of these systems. I'm going to try and pull that back and show you where I think AI is going, where I think HPC is going. I need to find a mouse here. There we go. And I want to talk about HPC as an architecture, separating it from HPC as a workload. In HPC, we get to talk about big science all the time. Satoshi actually had a better picture yesterday about doing drug discovery in molecules and so on. This one is important because it's actually running on ARM silicon in Bristol in the United Kingdom on a system called Isambard that I will show you a little bit later. Researchers there a month ago had not yet published the paper, but they were on the verge of publishing a paper about new discoveries with respect to Parkinson's disease on the left, and in treating osteoporosis, which is a bone density issue, on the right. So today, even though I claim that we're early on in HPC, there's real science being done at scale. That image on the right took 1 million core hours to simulate. Okay, so this is the standard things you think about for HPC. One of the projects going on at Bristol is this jet engine project, and it's got a name, if I can find it here, Asimov, that they are doing with Rolls-Royce. And I spent some time at Rolls-Royce talking with them about this. But this is your standard heavy-duty HPC simulation that has multi-physics with fluid dynamics and heat diffusion and electromagnetics and all of that coupled into a single application. And of course, the goal there is to try to digitally create a jet engine that is more efficient on fuel, less sound, more carrying capability, that sort of thing. This particular simulation is going to require an exascale of performance in order to be able to run it. So this animation is not yet a fully operational multi-physics package. So we talk a lot about HPC, and again, we tend to overemphasize the high end of HPC. And Satoshi yesterday actually compared his machine, this new Fugaku machine, to all of the cell phones sold in Japan. That machine is as capable as, I think he said 1 million cell phones, or maybe 10 million. So all the cell phones sold in Japan. I think lots of people don't get the scale of this, though. In the early 90s, I was at the Lawrence Livermore lab, and I was given the responsibility of touring senators through our machine room. And you can imagine that senators don't know a whole lot about computers. Questions would be, I thought computers were getting smaller, not bigger. And we'd show them, here's where the new computer's going, and it's going to be this big and that wide. And they'd go, I thought computers were getting smaller, not bigger. So I worked up an analogy that seemed to resonate with them. This is a picture of Lake Tahoe that I took this summer. Lake Tahoe holds about 40 trillion gallons of water, more or less, 10 to the 12th. In 2002, Japan with NEC released a system called the Earth Simulator that was roughly capable of 40 teraflops, which is roughly about one floating point, 64-bit floating point operation for every gallon of water in Lake Tahoe for every second. So if you've ever been to Lake Tahoe, 72 miles around, about 100 kilometers around, and it's one of the deepest alpine lakes in the country. That is kind of order of magnitude where we were close to 20 years ago. In 2008, we hit the petaflop scale. And to put it in perspective, the Great Lakes hold about 6.5 petaflops worth of water. So again, 15 years ago, the capability of the high end of these systems was one 64-bit operation for every gallon of water in the Great Lakes. And of course, we've dramatically increased that over time. This is a picture that those of us in high-performance computing like to trot out. This is the top 500 list for the past 25 years. The red line in the middle where it says n equals 1, that's the world's fastest machine at any given time. The list comes out twice a year, November and June. And the orange list, the orange line below it is what it takes to get on the top 500. So it's machine number 500. And then the summation of all the machines are what you see at the top line. So currently, the systems are such that it takes a petaflop of performance to get on the top 500. The top machine, which is at Oak Ridge National Laboratories, an IBM system with power CPUs and NVIDIA GPUs, is at 150 petaflops. And then the entire summation of the top 500 is just over an exaflop and a half. Exascale computing is kind of where the target is right now. So I want to point out a couple of interesting aspects here. The Earth simulator, that machine that was capable of one floating point operation for every gallon of water in Lake Tahoe, came out in 2002. And you'll notice that there's a bit of a step up in the #1 graph. High-performance computing has been quite political for a long while, and it's getting more so. When the Japanese released that Earth simulator, it made the front page of the Wall Street Journal, and there was a whole race on with respect to, similar to an arms race, there was this talk of ComputeNIC and how the US is losing its footing and no longer the world leader, that sort of thing. So you'll notice in here that there's kind of step functions going along where there's a breakthrough. You'll have a horizontal line where the systems seem to stagnate for a bit, and then there's a breakthrough. Without stealing Satoshi's thunder, I would expect that there's going to be a nice little kick up for him coming in the near future. The first petascale machine was an interesting architecture. It was at Los Alamos National Laboratory. It was called Roadrunner. It was actually done with the IBM Cell processor, which is, if you have kids, you'll notice that that's the same that's in the game station back then. And it was 138,000 cores, so it was quite a big system. And it was mostly a detached architecture in the sense that you had these cell processors that were quite a distant from the CPU, and programming them meant shuffling data back and forth and getting into algorithms that can overlap the computation with the shuffling of the data, and it turned out to be quite difficult to program. I will add in here, just out of interest, there was a machine in '09 from AMD that is called Jaguar. And the reason it's interesting is because 10 years ago, it was the #1 system on the top 500. And this year, ARM's first entry on the top 500 is a system called Astra, which is at the Sandia National Laboratory in Albuquerque. 10 years ago, it would have been #1. Now it is number 156. So if you take a look at my cartoon, the tip of the arrow there, the distance from that to the red square, that big distance, there's only 150 systems there. But the distance from the tip of the red arrow down to the orange line, there's 350 systems there. So this pyramid is very flat shaped. We always talk about the top 10 and the top 100 and so on, but it's very flat shaped. And of course, these are the systems that are spoken about publicly. There's a lot of systems that go into environments where they're not talked about. And I don't mean by that classified government environments. There is a bit of that, but there's a lot of commercial competition these days where an oil company or a bank will buy a very big system and then they won't report it out to anybody because computational capability is really a commercial advantage if you know how to take advantage of it. And that's kind of where we're coming in. So I want to underscore that these processors are not embedded processors, right? These are first-class citizens. This is a year old now, which in HPC is ancient, but a year ago, Bristol released these performance numbers where the ARM system, which is from Marvell, the ThunderX 2, are the green bars, and it's showing a socket-to-socket comparison, performance-wise, how it compares with the x86 state-of-the-art at the time. So socket per socket, the ThunderX 2 is outperforming Xeon processors there. But we do start with embedded processors. A lot of our HPC capability in ARM can be pointed back to the Mont Blanc project in Europe. So Europe is really a leader with respect to getting us into this market. Europe represents about a quarter of the HPC market worldwide. The US is about half, and Asia is about another quarter, roughly speaking, for where the dollars flow. But Europe is definitely a leader when it comes to trying out the new architectures. So there's been 3 rounds of the Mont Blanc project with hardware in each one, and of course, raising capabilities and software ecosystems to come along with that. Recently, with the help of Hewlett-Packard, 3 systems were installed in around the beginning of the year in the UK at 3 different universities. And these are 3 systems that are intended to help elevate the infrastructure and the applications programming capabilities on parallel systems based on ARM servers. They're all Marvell ThunderX 2 based systems. They're all from HPE. They all have interconnects from Mellanox. They all run SUSE as an operating system. So there's a lot of interesting work going on there, more public and more leadership oriented than we see in the US. Those are systems from HPE. Cray also builds systems, and if you're paying attention, yesterday the acquisition closed. Now HPE owns Cray, so now they're one and the same. But Cray also has installed ThunderX 2 based computers around the world, and this is one that is the one that I mentioned earlier with the drug discovery algorithms running on it and the jet engine applications starting to come up on it, and that's in Bristol. And this is the current largest public ARM system in the world, again based on the ThunderX 2 processor. So this is the one that's at Sandia National Lab in Albuquerque. Okay, a couple of shifts. The first thing is I mentioned that HPC is political. There are 4 very strong thrusts towards the exascale capability platform. They are going on in the US, in the EU, in China, and in Japan. Yesterday we learned a lot about the architecture going on in Japan. That system is imminent. They talk about having access to hardware now. Satoshi will talk about the ARM server-ready program that permits him to boot Windows on his big system. He even mentioned that yesterday, that he would be able to boot Windows. I don't know how Windows runs on 7.5 million cores, whether it's, anyway. I'm a BSD or Linux guy, but that system is going to be next out of the gate. One of the great things about the ARM business model is that partners can take the core IP and build that into what they want, and that's really foundational with respect to our interest in high-performance computing. I will talk a little bit about the EU activities. You'll see all the data here. I don't need to read it for you, but the EU is going down a path of an ARM-based system with an accelerator with it. China's interesting because they have 3 different projects betting on 3 different pieces of silicon, one of those ARM-based. And then the US is, I think, the most interesting because there was an x86 solution that was supposed to show up in 2018 and hasn't shown up yet. And the vendor is in the doghouse a little bit with respect to not delivering on that contract. These contracts, by the way, are hundreds of millions of dollars. It's probably got a dollar sign up by the Japanese target, but that was $1 billion investment to get that machine stood up. So the US will be interesting to follow, very interesting to follow. It's going to get hot and heavy in here soon. A few things about the Fujitsu machine. It was called the Post-K machine forever. It was 10 years in the making, just like the Earth simulator was 10 years in the making. We should not have been blindsided by that 40 teraflop system because the Japanese were very public saying, we're building this system, we're building this system. When they turned it on and ran it, we all went, oh my God, they built the system. Makes no sense. They told us they were building the system, and they did it. And so they're doing that again with the A64FX processor. So 10 years is a long time, but what they do in that 10 years is they dissect their algorithms. They know what they want to implement. They know how efficiently it needs to run. They know everything about the energy costs. They know everything about the software environment. By the time that machine is plugged in and turned on, it runs like a Toyota, right? It just starts up and goes. Some amazing performance numbers that they're coming out of that. The other thing that I wanted to point out, 2 more things, I guess. Satoshi yesterday said that this system has more bandwidth by an order of magnitude than all public cloud infrastructure today, by an order of magnitude. 8 years ago, he was at Tokyo Tech, and he stood up an HP system, and he wrote a paper that showed that that system had more bandwidth internally than the entire internet. Okay, so those are some big numbers. In high-performance computing, we are not scared of putting together millions of devices and making things work. And Satoshi is one of the world leaders in that. The other thing to point out is that I don't know that he mentioned it yesterday, other than he was talking about his facility. They turned off the K machine so that they can ready the facility for the post-K machine. One of the subtleties in there is they have plumbed 10 or 15 megawatts to that building. That's nowhere near enough for this new computer. This new computer is 40 megawatts. So part of their upgrading the building is to redo all of the electrical to take it up to 40 megawatts. When I was at Livermore, we stood up a building with 15 megawatts of power. And when I forked off a company to go do my own thing, they about doubled that and took it up to 35 megawatts. And everybody said, that's the ceiling, it ain't going any bigger than that. Well, 3 years ago, they took it to 60, and now they're taking it to 80 megawatts. So the lesson here is that electricity is one of the biggest components of these systems. What does ARM offer in this, right? ARM's background is performance challenged in an electrically restricted environment, right? So the designs that are in this community are very much anticipated and sought after by high performance computing. When we talk about electricity, the rule of thumb is it's $1 million per year for every megawatt. So Livermore is biting off on $80 million a year just to power the machine. Whether or not it's running an application, it's going to cost them $80 million. That's a big number, right? That's a big number in any budget. Okay, the next exascale project that is to watch closely is the European project. And these folks have the difficult task of bringing 25 countries together with different cultures and different languages and negotiating together to come up with an indigenous design for a processor. There's the obvious political undertones of that, but the more subtle piece here is the driver for them is to be in charge of their own future. If you roll the world forward and politics get to a point where countries restrict other countries from having access to technology, you really want to be in charge of your own IP and your own technology. So HPC, again, is an area that you have to tread carefully and you have to be very specific about what you're working on. So that's another project that's going to be super interesting to watch. I'm going to switch gears a couple more times on you. The next one is the HPC Software Ecosystem. ARM is really, really good at standards, really, really good at open source, and really good at partnering with people. About 3 years ago, ARM bought Alinea, which is a compiler tools group in the UK, and that forms a lot of the basis for how software comes together inside the company. But it is not lost on anyone inside ARM that a lot of the software comes from the community, and we really appreciate that. There'd be no way we'd be in this market without Red Hat and SUSE and on and on and on porting to the ARM system. We all believe competition is good. Having competition to x86 is very good, and we all understand what it takes to get there. Right now, one of the biggest poles in the tent is having to do with porting of applications and with ISV codes. We run into a number of situations where we go in to talk to an end user site and they want to have the PAM crash codes, they want to have all these different ISV codes available to them. So my ask to this audience, if you deal with the ISVs or you're at an ISV, we are super interested in helping you with that port, helping you find the customers, helping you find the early users. There's only 2 of us in HPC business at ARM, myself and Darren Cephalus, but we will take the time to meet with you and try to help prime the pump for those ISVs because they will turn into downstream activity for ARM. A little bit of motherhood and apple pie here. ARM shipped 21 billion chips. ARM doesn't ship any chips, right? I get a real kick out of all the people that say, that's an ARM HPC system. Well, it's really a HPE system based on Marvell products, but if you want to give me the credit, that's great. I'm in management, I know how to take credit, no problem at all. ARM is really, really solid in the embedded space, right? In the handheld space, all that sort of thing. The servers are where I'm spending my time, and I'm particularly focused on HPC, which is my background for 30 years, but also how that bleeds into the server space, because HPC on its own does not generally constitute a market. But HPC is a huge, good partner, like I said earlier. HPC will work with you, it will fund you, it will get you up on that surfboard, but you gotta have your eye on that next wave when you're doing it. So if you've seen any of the public talks lately, we've got a new brand called Neoverse. And a quick summary of that is that the Neoverse brand is everything to the left of Cortex, where Cortex is all the embedded and handheld stuff. Neoverse is meant to cover the fog, the data center, networking, storage, all of that sort of thing. And it was announced at TechCon almost exactly a year ago. And the argument that we make here is that with the explosion of IoT, the data flow on the internet is about to turn around. Right now, the internet exists to send you cat videos that you watch on your cell phone, right? Pretty soon, you're gonna find that 1 trillion devices, order of magnitude in the field, are all trying to send data to the left in this picture, upstream to the cloud. And there's a whole lot of activity going on as to how to do data reductions. You know, in the past, there's companies that have done content distribution. Now we're doing content reduction talks. And my alter ego here is that I've done a number of startups, and I've hung out with VCs and so on. And so I get to talk with startups about ideas in this space. And there's really some great ideas coming here. The one from an HPC perspective that I want to point out to you is in thinking about that wider base of HPC, not the top 100 or even the top 500, we are going to be seeing HPC-like activities moving out to the edge for latency purposes, for data movement purposes, for running algorithms that can do prediction better than your phone can do. There's a huge amount of opportunity in that space right now. So watch that space for these sorts of hardware devices and applications. The broad envelope here that you should be paying attention to is with a consistent ISA from the edge to the data center, you have opportunities to think about where that workflow runs and migrating that workflow closer to the edge and back to the data center. HPC is going to, the big HPC is going to remain in the data center and be the heavy duty bulk thing. But the concepts that we're coming up with are going to be pushing down towards the edge as the data is pushing up towards the edge. So it's really an interesting time to be working here. I think I will skip the argument HPC is an architecture versus a workload. The simulation workloads are what everybody sees by HPC, but there's a whole lot more there, and I want you to pay attention to it. And then I will just close by pointing out that we're very data-driven here. The Economist published that, Chips Everywhere, about 2 or 3 weeks ago, and they are starting to get on the bandwagon of there's going to be IoT everywhere, and there's all sorts of issues with it. There's all sorts of opportunity with it as well. But believe it or not, I ran into this CIO review just surfing the net the other day. I wasn't aware that our CEO was on the front page of CIO review talking about supercomputing. When I got up here, remember I said I own supercomputing at ARM? You'd think I would know about being on the cover of something, but I didn't. So, thank you for your time, and enjoy the rest of your event. Questions?
So I do have one question, and that
Surfing or Ho Chi Minh?
So yesterday, Matsuoka Sensei basically explained how they had the ceremony to shut down the K. And I sort of in my mind had that picture from 2001 when Dave is shutting down HAL, right, in the spaceship. But why shut it down? Is it that it's just not useful anymore? I mean, I know they needed the space, but they could build a new building. Is it the cost of the electricity to run it isn't worth it anymore?
It's effectively that latter bit. Think about where he's going. He's increasing his capability by 2 orders of magnitude for about double the cost of the electricity, right? So those two numbers together mean that the old hardware to him and his facility is not worth it. To somebody else, that hardware has value. So to pull another random example out of the air, Texas Advanced Computing Center goes through a lot of big computers. They turned off one of their systems a couple years ago and they shipped it to Portugal. And Portugal stood up a supercomputer because to them, the cost of electricity wasn't as prohibitive as the acquisition cost. And if you can get it for free, the shipping cost, then we've got some capability that we can start to prime the pump with.
So K will go somewhere. There's a second-hand market for HPCs.
It may, I don't know. I haven't talked to him about that. There's some interesting stories about a second-hand market for old Crays that, beer would get some pretty funny stories out of me with that because they have gold leads in them. And so people will buy them for the precious metals.
Thanks so much for joining us today. I really appreciate it. Very interesting. And now I'd please join in welcoming our next speaker from the University of Michigan. Did I get that right? Jeremy Helen.
Oh, hello, everybody. My name is Jeremy Helen. I am a research computing manager at the Advanced Research Computing Technology Services Group at the University of Michigan. I've been in research, academic research, for 23 years, and I've been supporting HPC and advanced research computing for about the last 15. I built my first HPC cluster 15 years ago. It was 256 cores and running DDR InfiniBand, and every system I built since then has been progressively larger and progressively bigger. At this point, I now manage 3 teams. I manage the data science team, which I'll talk about today. I manage storage, and I also manage a private cloud and enclaves team inside the university. So University of Michigan, who are we? Colloquially, we like to think ourselves as the Ivy of the Midwest, though I think several other universities might want to contest that. We have roughly 20,000 staff members, roughly about 50,000 or so students. We have roughly, about 5 years ago, we ran about $1.1 billion in research expenditures. And today, this last year, we ran about $1.5 billion. The University of Michigan has been investing heavily in academic research in a broad portfolio of research and expenditures, both in the health system and in the university proper. We're one of the few public universities with both a full health system and a university. And the other joke we have is that we're 19 schools and colleges united by a single football team. There's a diverse amount of research, a diverse amount of interests. The group I work for, Advanced Research Computing and Technology Services, or RTS, we provide comprehensive computational storage tools for university researchers. So we provide everything from high-performance computing. We also provide high-throughput computing on the same machine, which is HTC, for those of you who don't know. We provide storage. We provide big data and private enclaves, and we tie it all together with high-speed networking. We recently just took from Dell 14,000 cores of Intel HPC roughly about 3 months ago. We run 4 HPC clusters. The cluster I just mentioned. We run a restricted data cluster for people in the medical services and in people working with restricted data from the government. We also run a Conda cluster, or a cluster for researchers whose grant prevent them from using a shared cluster, and therefore they need to buy their own hardware for some reason or another. And then about 4.5 years ago, we acquired an IBM Power 8 machine. And so we have a diverse amount of hardware across Intel. We've run AMD clusters. We even ran a Power PC cluster back in the day. So we have a lot of experience with a lot of different things. We run roughly about 25 petabytes or so of aggregate storage. Our clusters run about 5 petabytes of Scratch. We run about 5 petabytes of high-speed storage. We have about 5 petabytes or so in what we would call a cheap and deep storage service, where we're balancing costs to the researcher versus performance to get and put the data in the service. And then we provide a data archive, roughly of 10 petabytes, that's all on tape. We provide an end-to-end storage service for our researchers, from data acquisition all the way to, I need to keep the data for 7 years so that people want to reproduce my results, they can come and get them again. Our goal at the University of Michigan is to make data easy to analyze, easy to move data close to the compute, but also be able to scale for the researcher who wants to do something very simple on 1 or 2 cores, all the way up to building a complex parallel job of 1,000 cores. And if you want to move bigger, then we're collaborating with Exceed and National Resources to go to people who want to do 10,000 cores or 15,000 cores. Whatever we build at the University of Michigan has to scale itself. So everything we build, from our storage services to our compute to our enclaves, we have to be able to add to it very quickly and very easily. And so we're going to add, when we add something new, we're just adding new nodes for HPC clusters. We're adding new storage nodes to our storage services. We're adding drives. We're adding tapes. Right? Everything we do has to scale very quickly and easily. Research, as I like to say, is a lowest cost business. If the government looks at a research project that's going to cost $40,000 or $50,000 to do the same thing, they'll pick the $40,000 version every time. And so from our perspective, from a researcher's perspective, they want services that have to provide a balance of costs and of performance. And that's what we look to do every time. So why do we look at ARM for data science? What does ARM bring to us? So when we looked at this 3 years ago and started this project, we were looking at the Cavium ThunderX platform. And it provided a number of interesting features that we were curious about. Each ARM machine, or each ThunderX machine, had 48 cores in a processor, 96 cores in a dual processor machine. There was rapid data flow between the CPU and the networking, allowing for basically no bottlenecks. Each node had 40 gigabit native on board, so when you're moving data into the system or out of the system, it moved quickly and efficiently. And finally, the ThunderX motherboard chassis provided enough high-capacity drives per node to provide a sizable HDFS for people who are doing big data problems. For the university proper, we believe that diversity in architectures drives innovation and research. By providing a new architecture to a researcher, they may come up with a novel methodology that they couldn't do on another architecture. And ourselves inside the office, we also like to understand new methodologies in research to stay competitive with other universities. So for us, in 2016, there was mutual interest between Marvell, or Cavium at the time, to explore ThunderX for data science in an applied setting. So we acquired 40 or so nodes from Gigabyte. It collectively provided us roughly about 4,000 cores, roughly about 25 terabytes of RAM, and aggregately 3 petabytes of HDFS, with really one singular goal. We wanted to build an analytics environment using common Hadoop tools for research use. At the time, we had a modest cluster that was close to our HPC cluster that was running Spark, the Spark Hive, PySpark and PySpark R, and then we were looking at the time Parquet to try to improve performance for researchers. And so we started with that very basic set of tools and moved forward. And because we had x86-64 experience, it seemed very straightforward. In fact, I think one of the first things we said early on was, well, it's Java, it's all Java, it should be really easy to move, right? Yeah, well. We did manage to build a working cluster. We had a short engagement with Hortonworks that was actually fruitful and built as a cluster. It was not supportable. It was not reproducible in any way, but we were able to make things go. And it was very encouraging to us that we could sit down and build a cluster very quickly. But we had to rebuild nearly everything along the way at the time. We discovered that the Hadoop architecture is just a complex stack of software dependent on each other to work properly. Those interdependencies make it very difficult to make changes, to make small modifications. And it took us some time, but we finally got somewhere after the Hortonworks experience to actually build something that worked. But we ran into two minor pain points, but still something that was significant for us. For example, libhadoop, the library that comes, it's a core library that comes with Hadoop, has bytecode dependencies on x86 that actually help with compression and provide performance benefits. These libraries don't really work on ARM or aren't really feasible. And so there was already a small performance issue that we had to contend with immediately. It was kind of painful, but it was something that could be worked around. There is this issue with a piece of software called protobuf that Hadoop depends on. And when we started, we were working with CentOS, and the version of protobuf that came with CentOS at the time was a more advanced version than what Hadoop was expecting. And we had some problems basically getting it working. We had to work back porting protobuf to get to a point where we can make it work with Hadoop. We still have to patch this to this day. It's actually one of those things that's kind of surprising that it still exists. I would like to say that when we built the first big cluster, we actually found some RPMs that were ARM available, that were working, that had basically been using Fedora, I think, Fedora 21 or 20 or something like that, that really got us over the hump in some of the final pieces to make this thing work. And so we didn't know where these RPMs really came from, and it turns out that we'd never really heard about Linaro, but we found a reference to the CentOS list, and it turns out that the RPMs we initially built with actually came from Linaro. And so we talked to Ganesh's team over in the Linaro group, and they've been extremely helpful to us in actually making progress at a rapid rate. We repackaged a lot of the RPMs that we had gotten to solve many of the problems we had. So, we've had, over further engagements with Linaro, we've been working very closely with them to get farther down the road. And when they went to Big Top, we've been working very closely with them to go to Big Top to move forward. And so initially, one of the other things we did that was a really interesting problem was we worked very closely with our HPC team. Our HPC team builds a cluster using Ansible. We don't use a lot of the common HPC's tools like Werewolf or anything like that. It's pretty much a custom in-house project. We use their Ansible toolkit to build our first data science cluster. One of the ways they solve their problems whenever they do a common upgrade is they'll burn down the computer, and then they'll just reinstall it using Ansible from the ground up. They'll disconnect Lustre so that Lustre, you don't have to worry about losing user data or anything like that. We did that the first couple of times when we built this cluster, but we discovered very quickly that it was fraught with peril because you can't easily disconnect HDFS. Right? There's always a chance that with HDFS you might burn, you might accidentally format over the drives on individual servers. We finally worked with the HPC team to build a system that wasn't burn it all down and start over again, and now we at least use yum update to bring up machines. But today, we manage the cluster with Ansible, and we do twice yearly updates, basically gradual yum updates, and it's a very smooth operating cluster. We started this project roughly in 2016. We were able to hand it to users in June of 2018, and we were in pilot mode through 2018 up until the summer, and we were in full production starting in May. And this semester, the semester that started in September, is the first full semester where we have full user base and full coursework running on the cluster. And so we have roughly about a dozen research groups and about a half dozen courses who are using the cluster for both teaching and learning and data analysis. We initially put on what we call the campus Reddit repository, which is a full copy of all the Reddit data, going back to the initial run of the first initial deployment of Reddit. And we use that primarily for teaching and learning and for internal testing. Recently, we onboarded the local campus Twitter repository, which roughly holds, which I'll talk about in a bit. But the initial use cases that we want to identify were based around social sciences. Social sciences are heavily underserved at the university. Social scientists don't really know anything about HPC, and they don't really do parallel computing very well. And so data science, almost all of their work is with data, with contextual and post analysis, and so for us it was very straightforward to introduce them to the Hadoop cluster. And quite a few groups have taken it, like a duck to water. They use it mostly, again, for contextual analysis, and one of the more interesting projects when we first deployed the cluster was fake news detection. Basically using, looking for emotional language in social media posts, and using that to try to detect whether or not this was, providing slanted news sources or whether or not it was a straight news reporting. We actually had a really great kiosk at supercomputing last year, if anybody was at supercomputing, where we basically put you up against our fake news detector that we were running our Hadoop cluster, where you could basically try to figure out if 5 questions were fake news or not. And by and large, it was about 50-50. It was kind of surprising. So our campus Twitter repository roughly is about, it's actually about almost a petabyte of Twitter decahost data now, which is 10% of all the data in Twitter. The data repository currently exists in a uncompressed form. We're currently in the process of recompressing it all into Parquet format. So it currently sits in the full petabyte on the Hadoop cluster. Interestingly enough, the whole thing actually compresses extraordinarily well, and we expect that once it gets compressed down, it'll roughly consume about 150 or 200 gigabytes when it's all said and done. We also have some researchers who've been contributing data over time. They drink from the Twitter firehose regularly, and so they pretty much will add the firehose data that they, to supplement the other data. So we've been bringing in roughly about 20 gigabytes of tweets per day into the system. And this is provided to all researchers across campus. They just have to provide the Institute for Data Science, a justification of why they want to have access, and they'll generally get it. One of the things I'd like to talk about is some of the projects that have been using the cluster to date. The first project that I'd like to talk about is a work by Dr. Romero and his student in the School of Information. And they've been using the Twitter repository and other social media to understand the effects of disasters on communities. They gather data from frequent public users and their local networks before and after an event. And they're really looking at usage. They're looking at, and they basically also want to do a longitudinal study, so they're looking at multiple events. And the goal is to understand how, who do people contact in the aftermath of one of these events? Does the circle that they talk with shrink or grow? Do they reach out to more public sources? And of those public sources, are the official sources, like government sources? Are they news media? Does the news media that they contact change from media that they contacted beforehand, or does it grow to reach a wider circle? Some of this work is both just drinking from the fire hose, and some of this work, my understanding is they actually will reach out to individual people in various places and try to, they'll either seed them in places or they'll get some feedback afterwards. The second project that I find very interesting that's been working with our cluster is a project in political science. And the goal is to measure policy diffusion. That is, how do bills and laws diffuse throughout the government system in the United States? And they've been working with data for 20 years, from 95 to 14. And they basically, I don't know the size of the data they've consuming, but it's a massive amount of data and a massive amount of laws. And they're basically they basically can build these textual comparisons and build analysis to understand how these things diffuse. And they've discovered that new policies are diffused through using Spark on our cluster that they weren't able to do with any other project, and that the earlier bills and laws are passed and start working through the system, the faster they go over time. And it's been extraordinarily successful for them. It's opened up further lines of research into patterns. I believe they're applying it to other countries, other places, and also looking into other fields to apply the methodology. I'd like to talk a little bit at this point about lessons we've learned in this project. This is, some of the things I'd talk about have been great for us. Big Top has been straightforward and outstanding for us. It accelerated our rate to deployment. The new CentOS and Red Hat packages that have been being deployed in the system is perfect for us because we need to provide an operationally supportable cluster, and we're a CentOS shop, and it's been very helpful. At this point, given Big Top, we think we can build a fully reproducible cluster in roughly 2 to 3 days or so if we were to have a major disaster. One of the things that we've been coming across is our researchers use Conda. How many people are familiar with the Conda distribution for Python? Okay, so Conda is a very popular open source distribution for Python. It is consumable multiple scales. We have copies installed in our HPC cluster by licensing through Conda, but individual researchers can download it at no cost. And it is a fully featured distribution for Python. I mean, you get Python, Matplotlib, NumPy, SciPy for all your computational needs. And researchers use this on a regular basis. Our researchers are used to this because it's on all our clusters. People can get it and put it on our private cloud or in our enclaves. One of the places that it's missing, and we've had a lot of requests for, is making these things available to researchers on our cluster. Is probably the biggest gap that we cannot currently fill in terms of software. One of the things when we were starting in 2016 that we had problems working with is that early packaging with software on the cluster was focused mostly on Debian, Ubuntu, and Fedora. And we're primarily a CentOS shop. We use CentOS because of stability and supportability. And some of it is also inertia. A lot of researchers expect to see, or expected at the time to see CentOS, and so it's what we try and really provide to our researchers. We spent a lot of effort and time early on translating our Fedora packaging to CentOS. This is not as much of a problem as it used to be, but the ability for the community to provide CentOS packaging, at least to make it easily supportable and deployable for us, is extremely helpful. One of the things that we've been hearing about, this is something that I'm not sure is currently a problem, but it is something that I want to bring to people's attention. And this is something that also is sort of the tip of the iceberg for us. So I'm going to talk about it more later. But Apache Spark is actually the software that we use on this ecosystem. And there's been talk about, in this PySpark community about not developing against ARM64 for future versions. If a developer all of a sudden decides not to deploy for ARM64, how do we convince them that it's in their best interest to keep going and keep moving forward? So as an organization, what are our future goals in moving forward? Our short-term goals are actually pretty straightforward. We're looking at Hadoop 3.0. There was a great talk that was given about Ambari earlier today that we're interested in, because I think we could use Ambari for metrics. But as a larger, long-term set of goals, social science data is really, it's the tip of the iceberg on data in terms of data for us on campus. The bulk of data that we see on campus is restricted in some fashion or another. Primarily, we look at health system data. So there are two sources of data that are restricted. There's health system data, and that is being made available to researchers for the first time at the university, which is basically the health system data warehouse. It's a modified form of all the patient visits, all the patient data that currently sits in our health system. And over time, researchers can start making requests for subsets of that data, and we'll be getting that data for analysis. The other bulk of data that we've been seeing is private claims data, either for private insurance providers, such as Blue Cross Blue Shield, or Optum, or other health providers, or it's public benefits insurance data, so like Center for Medicare Services or Center for Medicaid Services, a place like that. We get a massive amount of this data at the university, and researchers that get this data don't get it in small doses. They get data in terabyte lots at this point, right? Longitudinal data over 20 or 15 years. And from our perspective, from their perspective, they're starting to run into these barriers of being able to do this analysis on tools that they've traditionally been using it on. So this is R, SAS is a great example of something that people do this on. Hadoop, we think, is actually a great place for people to do some of the work they need to do. They talk about some of the analysis they do will take in SAS, they'll take 1 to 2 weeks on their desktop or workstation, and we think we can get that down to a couple days. So from our perspective, what do? We think we know what tools we have to provide. We just need to sit down and provide it. And some of it, so these are tools like Atlas and Knox and Ranger. And it's also going through a compliance framework inside the university to say, okay, you're now cleared to store this data here. Let's start working with it. The other type of analysis we're looking at, not just with insurance data, is also genomic analysis, which is becoming also popular as a part of precision health. So precision health is this idea that basically you can aggregate all these types of data, which I've, provider data, genomic references, patient registries, things like that, into one big data source for people to sort through. We just recently started a precision health initiative at the university, and they're growing pretty rapidly. And genomic analysis is going to be one of the toolkits that they need to do their work. Moving from the leading edge of work to bleeding edge of work, we know that at the university, the data analytics climate is rapidly changing. I think Strata last year, Strata last year, they said, Hadoop is dead as a joking thing. We don't think Hadoop is dead. Hadoop has its place, but it's becoming a niche place. We think that machine learning and GPU data analytics are taking the world by storm, effectively. Just as an example, our College of Engineering, where machine learning is currently the most prevalent, they buy these boxes that look a little bit like this. This is not probably direct analog, where they buy GPUs. They'll buy these 8-way GPU machines with massive PCI lanes. They'll put two 19 or 18 core Intel processors. They'll put half a terabyte or a full terabyte of memory. They'll put 2 NVMe drives to move the data in and out of the GPUs really quickly, and they'll run machine learning workloads on these. And they buy these things. They've been buying 3 or 4 machines at a time to do this type of work. One of the things that we find interesting is whether or not we could come up with an alternative methodology that doesn't depend on Intel on the front end, but depends on ARM. And we're looking at the work that ARM is doing with NVIDIA and the contract that was signed there, and whether or not that would be helpful to us. We do know that this goal requires a major shift in terms of hardware framework, because we know that or at least I've seen, as near as I can tell, there's no hardware infrastructure that can hold 8 GPUs and ARM processors right now. So this is something that we know there's a lot of work that needs to be done before it goes forward. So Spark, as I said before, is only really the tip of the iceberg. The machine learning ecosystem is dynamic and changing rapidly. The amount of machine learning software that's out there, right? Each of the big 3 cloud providers have machine learning software now. Google, Microsoft, and Amazon, plus a myriad of other providers. From our perspective, we provide a few tools, or we're looking to provide a few tools on whatever platform we provide. TensorFlow is very popular in our HPC cluster. Keras is out there as well. Past that, it's still this big churn. We don't, one of the things that's interesting is how do you pick a winner, and what winner that is a really interesting question to us. And in some ways, from our perspective, we almost always let the researcher decide. The researcher should tell us what they want, and then we provide that for them. There is a bit of give and take where if we come across something interesting that we know a specific research group, usually a larger group, is interested in, we'll point it out to them. But for the most part, we're providing what researchers are interested in. And I think an interesting difficulty for us going forward is trying to determine what best to build and debug and support when we move forward with our ARM64 for machine learning. So in conclusion, with partnership with Marvell, we've built a Hadoop cluster at scale for our researchers to use, and it's been extraordinarily successful so far. We're looking forward to opportunities to build and grow for machine learning going forward. And I have to, I can't stand up here today without thanking the 3 people on the data science team who have done all the work. Seth Meyer, Mark Patton, and Matt McLean, who have really just done an exemplary job on building this cluster. Thank you.
Thank you very much. Thanks very much, Henry. We really appreciate you coming here and sharing that with us.
Thank you.
So we're going to break now to start our day. Remember, if you're coming to the member dinner tonight, if you're invited to come to the member dinner, 6:45 p.m. at the Circle, and we're back here tomorrow morning at our usual time of 9:45. Have a great day.